Yeah, I don't, is this on? Okay. Okay, so yeah, so we're gonna start with the morning session. So the first speaker is Oliver Tse, is that how you say?
Yeah, that's
Tse?
right. Yeah.
Who will talk to us about quantified overdamped limit for kinetic Vlasov-Fokker-Planck.
Thank you. I'm guessing you hear me as well. Yeah. Good morning. I hope you had a restful evening. I personally did not, but but it was very good. I enjoyed the evening, and because I had to work quite a bit on this one. We'll see how it goes. And also this morning we had so much fun at breakfast that I almost forgot that the thing would start at 9. So yeah. All right. Anyways, so I'm going to be talking about quantified overdamped limit, and I'm guessing you've heard of the term overdamped limit. It's a pretty classical question. No, I see. All right. Okay. Before I start, if there are any questions in between the talk, just raise your hand or just simply shout. People in Zoom won't be able to hear you, but I will be able to repeat your question. That way they can hear you, and I will answer your question there and then. Does that sound good? Yeah? Okay. All right, so let's begin. Yeah, so this is joint work with Young-Pil Choi, who is in South Korea. Yeah, let's begin. All right. Okay. So what's our, if this works, I think I need to click there again. Yes. So what's the goal? We start with the kinetic Vlasov-Fokker-Planck equation. You've seen this yesterday. Well, at least something that looks like this yesterday. On the right-hand side, we have the Fokker-Planck term. So there is a diffusion term, and there is also a kind of like a potential, so an attracting potential for the velocity variable. And what it wants to do, so if this divergence in V, so that's in the velocity variable, what this wants to do is really send you into a Gaussian. So a local equilibrium for this one would be a Gaussian in the velocity variable, but then you have a transport term. And in this transport term, this is quite general. So we've decided to take something where it includes a confining potential of that form and also an interaction potential. And so this gives you your forces. Of course, with specific choice of K, you end up with the Vlasov or the what do you call it? The Vlasov-Poisson-Fokker-Planck equation, which is already pretty well studied. Over here, we use this notation to denote the first marginal of mu. So mu is a distribution over phase space, x and v. And rho is the first marginal corresponding to just this distribution of the particles, so the positions in position space. Okay, and what we want to do is we want to, this works, right? So send gamma to infinity. And when gamma goes to infinity, what we expect is we expect to converge to what we call the overdamped Vlasov-Fokker-Planck equation, or an aggregation diffusion equation, looking like this. Right? So you're carrying the forces over here, but then your diffusion in your velocity variable turns into a diffusion in the spatial variable. And this is also only an equation in the x variable. So this is really an equation on the level of the densities. Okay, and so this is the program for today. And this is what we're going to do. But let's start with a bit of a background. So where does this guy come from? So it comes from interacting Langevin dynamics. So you're given a particle system that evolves according to Newton's principle with some kind of forces, and you have a damping term here with this gamma variable. And remember, we want to send this gamma to infinity. And of course, you need some kind of balance between the damping and the Brownian, so the white noise here that's happening. So in fact, you get a Gaussian. Yeah, here again, the external and interaction potentials. And what happens when you take n and send it to infinity, you end up with this kind of a mean field limit, or McKean type Langevin dynamics, where you replace the empirical measure rho that was defined earlier. So maybe let me go back. So that's the empirical measure, just taking 1 over n of the sum of the Diracs at the positions. So here, this is where the empirical measure comes in. And if you send n to infinity, you end up with a limiting equation that looks like this. Okay. And of course, again, the goal is to study the overdamped limit, what happens when gamma tends to infinity. But before we do that, we have to rescale the system. What we have to do is we have to speed up time so that we can actually see something. So that we're going to do that. So we rescale time by gamma. and you end up with this equation. All right. And this is what we're going to study. So this is the kinetic Fokker-Planck. So essentially the same as before, except now rescaled in time. Yes, so mu gamma is now simply the law of these the process. Okay. Right, so this is our guy, and let's start by looking back into the past and see what has been done. So in 1940, about 80 years ago, Kramers was the first one to look at this and study this in some detail, but he used kind of formal asymptotics, and these were all done without interaction potential and for very specific external potential. This is just the quadratic potential that confines. And then Brinkmann kind of continued the work a little bit. And then Nelson picked it up in 67 and used stochastic calculus, so really using a pretty refined tool to study the Kramers problem, essentially the overdamped limit. Narita also took a similar approach using stochastic methods. Friedlin finally somehow solved the, I would say, he did the stochastic convergence, but also in the large deviation sense. So you also get really convergence in probability, also almost sure convergence of these processes. And then much later, in 2018, Duong and his collaborators, and this was done in Eindhoven as well, they used essentially taking ideas from large deviation principles, wrote down a variational principle for these type of systems, and was able to pass to the limit, but also providing quantitative estimates. But these quantitative estimates were, so the method they used were entropy dissipation type methods that they inherit from the large deviation principle. And they had to use some kind of a log Sobolev inequality to close the system. And for that, they needed some kind of convexity property on the level of the confined potential. Okay, and these were all done without interaction potential. And then, of course, there is a different community altogether who worked on this type of stuff. So these are hydrodynamic limits for the Vlasov-Fokker-Planck system. So essentially, when K is the Newtonian potential. Popper and Soller in 2000, they studied this problem. Goudon in 2005, Elghani and Masmoudi in 2010. And most of them, actually all of them, studied the case where you do not have a confining potential. So really just the interaction and the very specific interaction. So the Poisson interaction or the Newtonian interaction. Also, none of these were quantitative. So essentially really just using compactness arguments. And then variation, Dong again, using variational methods, was able to study the case with a confining potential and also an interaction potential, but required a pretty strong regularity on the interaction potential, and also using compactness arguments. So that means no rates as well. But what we want to try to do, or what we did, was to consider unbounded potential, so pretty general phis, still at kind of somehow quadratic at infinity maximum. We also considered singular potentials. So with repulsive potentials, it can be really Riesz singular, pretty singular. For attractive, we could almost touch Coulomb, but no, unfortunately. And what we wanted to do was derive W2 estimates. So this estimates in the Wasserstein distance. Okay, so maybe I will write down what the Wasserstein distance in a bit, in case you're not familiar with it. But since our work, there has been also other works that came out. So using a stochastic calculus, essentially taking our approach and translating it to the language using stochastic processes, Huang last year managed to do something similar. And then there's a related work by Jose Antonio and Young-Pil also and Peng in 2020, recently published, where they looked at the large friction high force limit. So what they do is they go from the system, but then with a non-linearity here. That includes the first moment, so the velocity field, and they send that parameter as well to somehow they first converge to the pressureless Euler equation, and then from then on they use the previous results of Jose Antonio, myself, and Young-Pil to show convergence to this overdamped limit. Okay, right, so enough about the history. Let's start by looking at very, very simple observation. So we start with, yeah, essentially this equation and rewrite it into this form. So how did I do that? What I did was essentially sum them up. So when you sum these equations up, these guys, they cancel. Okay? And so you're left with just dx, and I brought this over to the other side, over there. And so that's the equation we have on the underdamped limit, so the kinetic Vlasov-Fokker-Planck. And what we hope to get is something like this. So formally, what we'd have to control is this term. And hopefully this term, we can control it nicely so that it vanishes in the limit. Okay? So this is the general idea. Unfortunately, this doesn't work. So we had to try something else. Okay. So let's look a little bit at the overdamped limit. So this is the overdamped limit. That's the law of this process will solve the overdamped Vlasov-Fokker-Planck equation. And what we're going to do first is rewrite this into something that people in gradient flow knows. So rewrite this into a gradient flow formulation with some free energy. And this free energy is nothing but so the entropy that describes somehow the diffusion. So that's the linear diffusion over here. And then the forces, remember the forces are coming from potential forces. So that's the potential phi for the confining potential, and that's the potential K for the interaction potential. And so now we are in our very nice looking gradient flow structure. What we want to do next is, define first what we mean by a solution. So we have, this is kind of classical, but not really classical, but we have to define it. In any case, we call this an irregular solution if the solution is in W11 for almost every T, satisfies the energy inequality. But here we make a very strong assumption, asking that this object, so remember F is the gradient. So this is still a function of rho of the density, and we ask for this to be Lipschitz bounded. So what this means is we require somehow rho to be sufficiently regular if our interaction forces are very singular. Okay, so we require rho to be regular enough that this term can be so this irregularity can be compensated. Okay, and we ask for finite Fisher information. All right, so yeah, so we had our gradient flow formulation, and what we want to do is we want to find a map, kind of a map that translates our original problem into something that looks very similar to what we saw before for the limit problem. Okay, and this is what we're going to do. We're going to define first make an observation. Sorry, again we're going to sum up. We're going to sum this up as before. What we're going to do, however, this time is to do a change of variables. So we're going to define a new variable that as z, so x plus gamma 1 over gamma of v, that object here, we're going to define it as z, and we're going to rewrite this equation in terms of z. And we arrive in this equation. And then we're going to take the law of z. Okay, so when we do this, we arrive at something that looks very, very familiar. It's almost like the guy in the limit that we expect, okay, except for this term here. So there is a flux that is somehow not the same as the flux you want. Okay, and this flux depends on the kinetic variable, so it depends on mu, so the solution of the kinetic Vlasov-Fokker-Planck equation. But the good thing is that it looks so familiar, it looks so similar to the overdamped limit that we can actually use this. All right, so this is what we call the intermediate system. And recall, this is what our overdamped limit looks like. So what we want to do is we want to rewrite this and bring it into this form. Okay, all we did was add and subtract, nothing more. And now what you see here is a question about stability, because this equation is pretty much this equation except for this guy. Of course, everything that happens in here is nonlinear. So it's not, I can't just subtract them and then do something. So I have to do something smarter. Okay, so let's look a little bit closer at this equation. For this, we have the following result. And the result states that if rho were to be some satisfying some regularity assumptions, but we'll have to specify that later, but the same regularity assumptions as an irregular solution. And additionally, this velocity field, so E, so this is the error field, or kind of error velocity field, is bounded in this way. Then what we can do is we can take the, maybe, how many of you are unfamiliar with the Wasserstein distance? Does everybody know the Wasserstein distance? Yeah, okay. I don't have to write it down then. I mean, if you're not familiar with it, let me know so I can just write it down very quickly. Yes. Okay. All right. So what is the Wasserstein distance? The Wasserstein distance is the distance. Maybe I'm going to write it here that way. I don't have to. Yeah. So this the Wasserstein distance is. Or maybe I have it on the board, and everybody else can use it. If yeah. Okay. So we have W2. I'm going to write a squared here between two measures, mu and nu. Mu and nu are probability measures on, say, here in this case, RD, but with a finite second moment. And the Wasserstein distance can be written as the infimum over pi in a capital pi, and I'll describe what pi is later on. A double integral and x minus y squared little pi dx dy, where so capital pi contains little pi's that are probability measures over the product space, such that if I were to integrate somehow pi over just dot, say dy, this gives me the first marginal, so mu. And if I were to integrate over dx dot, this gives me the second marginal. Okay, so another way of looking at this is essentially the expectation of random variables xy squared, where xy are joint distributions in this little pi. Does that help? Yeah? Okay. And there's this very nice calculus you can do if you would take this Wasserstein distance and try to do some calculus with it. What we'll end up with is this inequality. And this is very familiar to maybe people who work in gradient flows a lot, especially gradient flows in metric spaces or in Wasserstein spaces. You see that if you were to take the time derivative of the Wasserstein distance squared between rho bar gamma, which is a solution of this intermediate system with any arbitrary measure, nu, and then you can bound this from above by the differences of the energies. So energy at nu minus energy at rho bar minus, this is this thing that we call the modulated interaction energy. Where does this come from? This comes from the energy. So let me write down the energy again. So the energy is rho log rho dx plus phi rho of dx half rho dx. Okay, so this is the energy, and the modulated energy comes from this guy. So there's a quadratic term here appearing. So there is a rho, and there is also an additional rho due to this term. When you do this calculus, you end up with a modulated interaction energy. This is this dk. And then you have another term here, just the Wasserstein distance again, plus this squared of the L2 of the velocity field. And this is a weighted L2 because you're taking L2 with respect to the, you can think of this just as the energy corresponding to the flux. So this flux. Okay, and so this holds for essentially any flow looking like this with some E. And then what you can do is you can compare the two. So here we have our intermediate system, and here we have our overdamped limit. And what we want to do is really see how to compare them. Well, this guy doesn't have an E, but still we can apply the energy variation inequality as before, as what I showed before. And we obtain the following result. So now we can actually compare the difference, or the distance, the Wasserstein distance squared between these two objects. So between the solution of the intermediate flow and the limit flow. And when you do this, all you end up with is this term. So this is the modulated energy. And then you have this still Wasserstein term, and you have that error term. Okay. So maybe let's do a very short proof, because the proof is so easy. So you take the two energy variational type inequalities, they look like that, and then you apply a very general principle. And the very general principle you can read up in maybe the book of Ambrosio Gili Savare, that tells you if you take the time derivative of the Wasserstein distance between these two guys, that's the same thing as taking the time derivative of the Wasserstein distance in one of the guys, fixing this, take that and evaluating at that time, plus the other way around. Okay? So what you're doing is you're just summing up these two terms for arbitrary news, and you're inserting whatever you want to insert, and that's the idea. Yeah, that's really, this is where this comes from. This comes from. Okay, so now we have a stability. We're almost done. All we need to do is check what this guy is doing, and check what this guy is doing. All right, because once we have control over this two terms, then we can apply Gronwall and close. Okay? So this is the strategy. Any questions so far? Okay. All right. So like I said, there's a couple of things left to do. Yes, we also have to say something about the distance between the Wasserstein distance between the original, so not the guy from the intermediate one. So the original density coming from the Vlasov-Fokker-Planck and the intermediate one. So remember, what the intermediate one comes from doing this shift. We have this coarse-graining map that shifts the space and velocities accordingly to get this guy. And now we have to compare the two. So the next thing we want to do is relate somehow this object with the Wasserstein distance again, and to get quantitative bounds for this error term. Okay, so let's start with the first one. Well, the first one is not too difficult. Just using kind of the definition of the Wasserstein distance, you will be able to get this bound. So so here I'm infimizing over all possible couplings, but in order to get that bound, I'm choosing a very specific coupling. So what I get is that the Wasserstein distance is always bounded from above by the specific choice of coupling that I made. And if you were to do that, you end up with this bound. Now, the difficult part is, in fact, controlling this guy independently of gamma. And this is something that we've actually not really seen before for this type of equations, particularly with singular interaction potentials. And so this was actually a lot of work to show and prove that we can bound this guy independent of gamma. Yeah, so this was the question that we had to ask ourselves. And I mean, I'm in this inequality, I'm hiding quite a bit, but we do get an inequality looking like this. So if F, so the force, remember, so this is the force which includes the potential and the interaction energy. If it is bounded from above by something linear, so if it's linear, at most linear at infinity, then there exists constants alpha beta, such that the entropy between the mu gamma and the Gaussian in 2 dimensions, plus the Fisher information, but only in the v variable, is bounded from above by this constant. So if we can make sure that this guy is uniform in gamma, then everything else on the right-hand side is uniform in, on the left-hand side is uniform in gamma. But what we also know is that, well, if this is uniform in gamma, I have a gamma squared there. So what you're going to see happening is that this term necessarily goes to 0. And this is what happens when you send gamma to 0. So what you're going to observe first is that the velocity variables will equilibrate very quickly to local equilibrium. They're going to equilibrate much faster than the global dynamics. And so that means what you will see is something looking like this. So the mu of gamma, as gamma tend to infinity, will look like the rho, which is just the density, times a Gaussian in the v variable. Okay? But what's more important is, in fact, this term right here, because this term gives you control of the moments uniformly in gamma. So this term can be bounded from above by some constant times 1 plus this entropy. And this is a result by Donska-Varadan, or yeah. All right. And now we have control of the velocity. But maybe just let me also make a note that you not only have control over the velocities, so the second moment in the velocity variable, but also in the spatial variable. So if I were to integrate this in x squared, then this is giving me the second moment also of the density variable. So rho gamma also has uniform second moments in gamma. All right. Yeah, so our next step is to relate this object with the Wasserstein distance. And let's recall, so this object is just, so we have the kernel, so the interaction kernel over here. We have the differences in the measures as measures. So that guy is a signed measure times again a signed measure. And this object will give you something, right? So, okay. So the first result is that we can bound in modulus the modulated energy with just the gradient of k. So for k regular, meaning that the gradient of k is Lipschitz, so pretty smooth. By the Lipschitz norm of the gradient of k and the Wasserstein squared. So this is a computation that you can do by just splitting this apart and using kind of a choosing again certain couplings in certain forms. The next one is the purely repulsive case. So if you have something that is, if your particles are purely repelling, doesn't matter how singular it is, what we know is that this has a sign. And this, in fact, has a good sign. Because if D is non-negative, if you look at the inequality above, I can just drop it. So somehow, repelling particles are doing better. And then we have attractive Newtonian. So this is where you have really the Poisson. Sorry about that. Are we good? Okay. So this is the case where you have the Poisson. So where the second derivative of k is just a delta Dirac delta at 0. And then it turns out that you can relate dk with the h-1 homogeneous norm. And there is a very nice result by Perrier that tells you that, in fact, this norm can be controlled by the Wasserstein norm, or Wasserstein distance, if you have upper bounds. So this is something that we have to show. We have to show that our densities are L infinity. Okay, so once you have this, then you can, in fact, get an inequality looking like this. You can put it in there, and as long as these guys are bounded from above uniformly in gamma, you're safe. And then we have a case which nobody actually really studies. So we have this weakly singular case, and this is the case where the Hessian of k is only L1. So this, of course, Newtonian does not fall here because the Hessian of k would be a delta distribution. But this one is slightly less singular. So in this case, in fact, you can control again the modulated energy by the H1 homogeneous, H-1 homogeneous norm, and something looking like this. And it turns out that this guy you can control because of this regularity by this. So you can pull out a Wasserstein again but incurring only the Hessian of k in L1. And when you do this, you end up with, so when you do this, you end up again with, so using this bound and the Perrier bound, you recover the Wasserstein. So altogether, you get a quadratic Wasserstein. So it's very essential that we get something quadratic, because everything here is quadratic. In fact, what we expect in our results is somehow that the convergence happens linearly in gamma. Okay, so yes. Just a short remark, dk is additive in k. So what this means is that you can take your k and you can play around. You can slice your k, you can add something repulsive, attractive, you can do whatever you want as long as all of these are satisfied. Okay. All right, so now we're okay with this term. So this term is just controlled by some constant, assuming again that you can bound the L infinity norm of the measures uniformly in gamma. The last one is to control this bound. This bound you can control in the following way. So if you were to write this norm down, the norm squared, then it's represented by this. So you can be bounded from above by this object. And here you see that it requires some kind of Lipschitz continuity here. So in the x variable, but also in the rho variable, so Lipschitz and if you want to extract the Wasserstein out, you hope that f would be also Lipschitz in the Wasserstein distance between the two measures. So if you were to do this for, if f were to be jointly Lipschitz, again, with respect to the respective topology, then you end up with something looking like this. And then again, you're on the safe side, because this object can be controlled by the Wasserstein plus some error term that you know will vanish. Okay, so that's of the order 1 over gamma, because here you're again, so this is the first thing we control, right? So this is the difference between density coming from the original Vlasov-Fokker-Planck with the intermediate density. All right, but of course, in general, that is not so easy, because asking for Lipschitz continuity with respect to the Wasserstein distance requires regularity, because we have singularity. And so what we had to do, so here, these are assumptions on now really the correct assumptions on phi. So we asked that phi be locally Lipschitz, the gradient to have maximal linear growth at infinity, and the gradient of phi, the Lipschitz bound for gradient of phi is bounded. So there is a bound on the gradient of, well, the second derivative of phi, essentially. And the second point is an assumption on the interaction potential. And the gradient of k is required only to be in LQ loc, so locally LQ. But outside some ball, so we require quite a bit. We require that it's quite regular. So you think about anything that is just very singular at the origin, but smooth outside. Okay? So roughly. And for these cases, we can show that, in fact, this object is bounded by 1 over gamma times some constant. All right, so so just as examples, we can cover the Riesz potential. So these are the repulsive Riesz potentials, alpha ranging from -1 to d minus 1. Wait, let me see. Yes, that's true. Yeah, and then for the attractive case, we can cover. This is not true. This should be an open bracket, and that should be a closed bracket. I'm sorry. So we cannot cover Coulomb, right? So Coulomb would be this case, d minus 2 for attractive. Okay. Right. So let's come back to our stability estimate. What we found out is that we can control this term again with the Wasserstein squared, and that term with 1 over gamma squared, and we just apply ground law, and we're essentially done. Okay. So let me just summarize with the formal statement. Under these conditions on phi, mu gamma is a solution, sufficiently smooth solution. I did not mention what type of solutions I'm looking for, but it's in the paper, and it's a bit complicated to write down. But anyways, you can find smooth solutions for the kinetic Vlasov-Fokker-Planck equation, and rho being an irregular solution of the overdamped Vlasov-Fokker-Planck. if the interaction potential K satisfies one of the following conditions, so essentially the one that controls the modulated energy, so the D term, if you remember. So if it satisfies one of the following conditions, then we end up with this result.
So you can treat attractive Coulomb.
So the question was if we can treat attractive Coulomb. So this is attractive Newtonian, so not really Coulomb.
But I'm confused about the distinction too, actually. To me, Newton and Coulomb is exactly the same force.
Okay.
Yeah. So what do you mean by Coulomb and what do you mean by Newton?
It's 1 over r squared, both.
But in which dimension?
In 3D.
Yeah, I mean, if you go up to different dimensions, I'm guessing you have a distinction between the two.
Okay, so it's because it's in general dimension.
Yeah, this is in D dimension, so we are in any dimension.
Okay.
Yeah. Yes.
But yeah, I mean, they're the same physics. It's exactly the same physics, whatever dimension.
Yeah.
Okay, maybe there is a.
But maybe you can write them down what you call Coulomb.
Jose wanted to say something. Yes, Jose.
No,
You mean so? I see, but okay, I see. I thought okay. I thought well then I was also confused. So I'm guessing Coulomb means repulsive, purely repulsive, and Newtonian means purely attractive.
No, because Coulomb, if you have plus and minus, they attract in Coulomb.
Yeah. So I mean.
It's a terminology thing.
Yeah, I guess it's okay. So I guess Jose has a different terminology than I do, and then you guys.
No,
but
we were thinking it's the. Yes.
Okay.
We were thinking the exponent matter, but for you it's the sign that matters between Coulomb and.
For me, it's the exponent, but I'm guessing I'm wrong there. I thought Coulomb is a very specific exponent and not dimension dependent. So that was what I was thinking. But
no, it's always
okay. All right. That yes, you. Yes, so the question was if we require the control of rho in L infinity. Yes, it is important. And we do require the control of rho in L infinity. It's if you look at the notion of irregular solutions, then we require the force to be Lipschitz. But if we want the force to be Lipschitz, then implicitly we require that rho is L infinity. But the reason why we don't make this a strong assumption is because if the interaction potential is smooth, then you do not need any control of rho. Do you see my point? If the interaction potential is singular, then you will require that rho is L infinity. Yes. So this is well, there are multiple ways of doing this. Either you prove it, or you prove it via mu. So we actually have an existence result saying that if you start with nice initial data on the level of mu, actually it's easier to prove it directly for the gradient flow, but for mu, anyways, you have to prove it for rho bar. I think it's very important to prove for rho bar. And this we have a result that says if you start sufficiently regular for your initial data, I will show you in a bit. Yes, I will show you in a bit. I have a safety slide just in case this comes up. But yes, okay. Yes. So let's summarize very quickly. So what I wanted to achieve was something from there, and I wanted to converge to this guy. And right. So if you were to take the first marginal, you end up with this rho gamma. That's the thing that we have. But then what we did was we first introduced a coarse-graining map. We did a shift. Remember this map, and we obtained the intermediate system or equation that looks very similar to this. And then we applied a couple of, so we also proved that the Wasserstein distance between the two solutions, they are of order 1 over gamma. And then we applied a couple of tricks due to the energy variational type inequality. If you control the two terms that we required to control, then you can apply Gronwall's inequality to obtain a solution of this guy. Okay, so this is this link over here. But Yes, maybe let me, so there are a couple of questions, but maybe we can go to that later on. I don't want to say thank you yet because I want to move on to the next slide. And this is the slide that, that you were asking for. So quite technical, but if we have that the gradient of K is in LQ log, so this is pretty singular. Far from the origin, we assume that it's smooth, so we don't care what's happening at the far from the origin. And if mu0, so the initial data, is in this space, so it's a probability measure with a finite second moment, but has a Lebesgue density, and the Lebesgue density is in this class of space. So this class of space are pretty much Sobolev type, but with a weighted norm, and the weights are coming from this what I call the Hamiltonian, so this object, because it can be that phi has quadratic growth, so we really have to confine this. But if the initial data in this sense is uniform in gamma, then there exists a positive time, so local solution. We could not globalize this, and a weak solution, so in the distributional sense, such that this is uniform in gamma as well. So we get also propagation of the same bounds in time for a short time for these quantities. So now if you were to choose P to be larger than D, right, then this will give you so in this, even in this weighted space, it will give you a Sobolev embedding that gives you that ends up in L infinity. So in general, it's very difficult to control the kinetic. The X variable is very difficult to control somehow. There is, I don't know if there are results about maximum principles or for kinetic equations for the X variables. So if I'm not sure if this exists. So what we had to do is we had to really ask for regularity, propagate regularity, and do Sobolev embeddings to control the X variables. Does this answer your question? Yeah. Okay, then I go back here and say, thank you.
Okay, thanks a lot for the very nice talk. Are there any other questions?
So you mentioned that
I guess the mic has to go there. Yeah.
Yeah.
So thank you for the talk. And so you mentioned in the end that you can propagate regularity only for short times. So your result, the convergence result holds for short times, or?
Yeah, unfortunately, well, it turns out that this time depends on the gamma, because what you expect is that when gamma is going larger and larger, you're getting closer to the diffusion, and in the diffusion you expect somehow global solutions. So if you expect global solutions, then you can extend this time, but this depends on gamma. But for the moment, we just say we have a fixed time independent of gamma, which you can choose for gamma large enough. So it increases monotonically, but you just say, okay, I'm going to cut here for gamma larger than some amount, and then you're done.
But your time goes to infinity with gamma. Is that it?
You can take it to increase, like as gamma is getting larger, because it is some type of a Grunwald, but then with a nonlinear term. So the explosion happens depending on gamma. Yeah.
Sorry, dumb follow-up question. Sorry, don't you cover cases where the limiting equation rho t can actually blow up in finite time?
Yes, if you expect global solutions, then this is the thing. But if you don't expect it, you cannot anyways. Yes.
Yeah.
Hello, so thank you for your talk. I was wondering, so you are saying that it's only the attractive case of the Coulomb potential that does not work. So the case where the interaction forcing the terms to be like the particles to be close together, right?
I'm not sure. I hear you.
It's not working.
It is working, but I think just louder maybe.
So you are saying that it's the case of the attractive Coulomb potential that is not working, right? That you cannot reach.
Yes.
Is it because of the regularity of the rho, or is it? Is it because just a question of regularity uniformly in gamma, perhaps? Or what is the main reason for which, the main inequality that is blocking in the?
Yeah, so of course, if you ask for more regularity, then there is a chance you can shift the derivatives to the row. But then I don't know if it's possible to close the system.
So for example, would all your things make sense also if the potential was log Lipschitz? I mean, if the mean field potential was log Lipschitz instead of being Lipschitz, as it is done like in the Le proof for uniqueness of Vlasov-Poisson.
Yeah,
like that.
So this would be interesting. I mean, this is actually a question also like, yeah, when do we expect somehow nonlinear convergence? I mean, this is linear so it's like 1 over gamma. This is super boring. But can we expect something different? And this, I'm hoping that we can, if we don't ask for too much regularity and try to work with with less. But yeah, this is something that I want to also figure out. Yes.
Okay.
Yeah.
Okay. Are there any other questions? I don't know how to get you the microphone.
Thanks for the nice talk. So I saw that from the original kinetic equation, you try to do a shift variable to get to some new formulation which resembles limiting gradient flow. So I'm curious whether your formulation can be applied to design some numerical method which behaves nicely in the asymptotic limit. Does that make sense?
It does. I haven't had enough coffee. So you want a numerical scheme on the level of the kinetic equation.
Yes.
That makes use of this coarse-graining map such that the convergence works. So there is a, okay. Very interesting question. I have never thought about it. I'm also not sure if this is, I don't, so the only thing I can think about is a splitting scheme, because you have to do, if you want to do this coarse-graining map, I don't know, because this coarse-graining map is really you're taking, from the point of view of trajectories, you're doing a change of variables on the space. But then this is depending on gamma. Yeah, I don't know. I'm sorry.
Okay, thank you.
But it's very interesting. Yeah, thank you.
Okay, are there any further questions?
Thank you. So going back to the inverse square law, right? So it seems that in many cases, I mean, this is one example here, but also if you do like, Stricher's type estimates in functional analysis, you always can go like up to the inverse square law, but you don't really capture it. Is there sort of an intuitive reason? I mean, why this is the case, in the sense that, is there some physics that you have in the inverse square case that you don't have, sort of, if you have like, 1 over something to the power of 1.8. Might not be an entirely well-posed question, but
yeah. Yes, there are many ways to answer this question, but I can't think of a very a favorite one. No, yeah.
So to phrase it differently as a physicist, whether it's attractive or repulsive in a plasma, for instance, you could have a purely repulsive plasma, purely attractive plasma. It's exactly the same phenomenon. Debye shielding, everything is exactly the same. There's no difference, repulsive, attractive, whatsoever. And so what's special about attractive?
singularity? I mean, you
So
kind of.
why singularity?
So I'm guessing if you take particles and then you let them attract, what they're going to want to do is try to form a delta.
Because there's conservation of momentum and angular momentum. You cannot collapse. Otherwise, all the planets fall on the sun. I mean, there's no singularity.
Yeah, sure.
So that's why I'm saying physically, it's exactly the same phenomena. It's just confusing mathematically.
It's just that nature fixed the law.
No, okay. So so this thing, what I'm showing you is more kind of on the level of the overdamped dynamics.
Okay, so that's why they speak
So
of damping.
For the overdamped limit, you do really have this. But for the underdamped, it's not clear for me, really. Yeah.
Still the dynamics of plasma for sun are still different than the attractive case of form galaxies. Right? It won't.
Yeah, in the repulsive case, the galaxies won't be formed, right? Somehow,
No,
yeah.
I disagree. I form galaxies in the repulsive case all the time because there's an equal.
But you have what do you have there? Like a.
More similar than you think, but it's not the same.
Not exactly the same.
Okay.
These are all super interesting discussions, but
Yeah. So if there's no further discussion, well, we can keep discussing, but let's stop the official. Let's take a 5-minute break and then the next talk. So let's thank the speaker again.